Good morning, everyone. I will be chairing the second session. It's close to 11:15. We'll start the program now. As we had the program, the abstract book first two pages save the program so you can go through them. All the speakers have been given 25 minutes, and then there's a separate 5 minutes given for discussion. So I request all the speakers to stick to the time. And as we are recording all the lectures and question answers, in case you have any question, please wait for the mic. If the speaker and others could hear you, it would be good if you have the mic so that all the questions could be recorded. The first speaker in this second session is Prof. Wategoankar from TAFR. The title of his talk, as you can see, is Nothing Improper About the CH5 Hydrogen Bond. Sanjay, you can start.
So let me begin by acknowledging the initiative and all the hard work Arunan has put in putting this event together, putting the issue of the 100th issue of the Journal of Chemical Sciences. And thank you, Arunan. And thanks for inviting me also to participate in this function. So, as my title of my talk is up there, and see, 100 years and still counting, we know a lot about hydrogen bonding now, at least that's what we think, but Arunan's page, the program face shows that's still an elephant that we don't know what it is. I tried to copy that and try to paste it here, but somehow I could not do it because this is, I don't know what trick you did. But anyway, so this is the picture is, the traditional conventional textbook definition of the hydrogen bond is that we have the two hydrogen atom bound to electronegative X atom. There is a dipole, there is a polarized bond, and then when it comes in contact with the electron rich substance, there is an interaction between this positive hydrogen and this Y. Now we know a lot more than what we knew then. Some of the electron density moves into the anti-star orbital of this, and also there is evidence that the electron density is built up between the hydrogen and the Y. And as a result of this, the XH stretching frequency redshifts. And these are called conventional or the classical hydrogen bonds. Now, last couple of decades or little more than that, we know a different kind of hydrogen bonds, namely the unconventional hydrogen bonds as I call it. And these are because these are mainly sulfur centered and the carbon centered hydrogen bonds, because the electron negativity difference between the sulfur and carbon and hydrogen is not very great. So, therefore, these bonds are not very activated, and so these are the examples of some of this sulfur centered hydrogen bond, and the carbon centered hydrogen bond is very peculiar that it shows blue, red and zero shifted hydrogen bonds, which is kind of a very unique of the carbon centered hydrogen bond. And because of this, there have been a lot of arguments between the referees and the writers, the people who author the manuscript, whether to call them hydrogen bonds or not. And Arunan got irritated by this, and then he decided to form a task force and redefine the hydrogen bond. There have been many traditional definitions of hydrogen bond from Pauling, Pimentel, etc. But this group of people came up with the so-called latest definition of the hydrogen bond. It's a very difficult task, I would say, but then the important thing is that there should be evidence for the hydrogen bond formation, and there are many things in this article, and they are given some 6 criteria. One of them, namely the first one says that the conventional ones are the electrostatic, but one should also realize that there could be dispersion dominated hydrogen bonds. Criteria says that the length of XH bond increases and leading to a redshift, and there is a footnote on this which says that certain hydrogen bonds in which XH bond length shortens and the blue shift is operated. So, this is more inclusive definition of the hydrogen bond. So, let me talk about then the CH hydrogen bond, which is the topic of my interest and has been now. Although the hydrogen bond is 100 years old, the CH hydrogen bonds are also not new. They have some more 80 years odd history, and you can say from 1935 onward there have been mentions about this kind of interactions in the HCN liquid. Here it is the mixture of haloforms with acetone, so on and so forth. And in 1960 book, he said, Pimentel and McClellan, in summary, the evidence in favor of association of chloroform is with basis is conclusive, and thus it must be concluded that in this instance CH group can serve as hydrogen bonding acid. This was 60s, and then in 62, based on the crystallographic data between purine and pyrimidine crystals, Sutter had said that based on the distance constraints, these are hydrogen bonding interactions, which was heavily criticized by a group of people, and they were arguments about the distance constraints on the C and O distance. Later, of course, there was a refined data, and then it was indeed confirmed that the CHO interactions can indeed be the hydrogen bonding interaction. Desiraju and Mascal, they based on the statistical analysis, they conclusively said that the CHX interactions are indeed hydrogen bonding interactions. But these are all structural data, there is no spectroscopic information here yet. However, there had been instances of spotting the blue shift in the CH in organic synthetic people where they monitored the CH frequencies, but they never thought of that in terms of the hydrogen bonding interaction. So, the first evidence in the isolated complex came in 1999 when Pavel Hobza and Bruchy, they published their work in the fluorobenzene chloroform complexes, and they termed this anti-hydrogen bond between chloroform and the fluorobenzene. These are the computationally optimized structures, and based on the rigorous analysis, they assigned this structure to the observed conformer, and where the CH stretch was blue shifted by 14 wave numbers. Now, after that there were another example of benzene chloroform, there also the CH stretch of this chloroform was blue shifted by 15 wave numbers. So, this is the first isolated complex in gas phase identified as a CHX or CHY hydrogen bond which is blue shifted. There have been some cold matrix data. A group in Belgium, Van der Weken's group, they had carried out a lot of work on this dimethyl ether chloroform complex where the blue shift was observed. The interesting thing here, they had these mixed haloforms where the chlorine and fluorine forming the hydrogen bonds with dimethyl ether. As you increase the number of chlorine atoms at the cost of fluorine atoms, the shift changes from blue to red. If you increase the number of chlorine atoms, it goes, if you increase the number of chlorine atoms, it goes from blue to red. So, fluorine atoms cause blue shift, chloroform chlorine atoms cause the red shift, and the intensity changes from decrease to increase as you increase the chlorine concentration. So, that is not the end of the story. Of course, there are many theories to jump into this, and there were theories such as excess contraction due to short range repulsive forces, so to speak, that the Y as it comes closer and goes closer, the CH feels compression and that causes the blue shift. Electron density transfer to the remote parts of the XH, namely not only the CH but maybe the other 3 chlorine atoms or the F atoms. Electric field effect by the Hermansen et al. And the S characters, a number of different models proposed for explaining the blue shift in the hydrogen, CH hydrogen bond. The twist in the tail comes when this paper in 2004 says that it is not the blue shift is the characteristic of the CH hydrogen bond, but this is the tetrafluorobenzene water complex where the CH stretching frequency bound to this fluorobenzene hydrogen was red shifted by 8 wave numbers, and also in chloroform methanol tetrafluorobenzene, it was also red shifted by 12 wave numbers. So, now it is clear that the CH hydrogen bonds, they have both red shifting variety, blue shifting variety, and one does not know as to what exactly is the situation and when does it do it, can you predict it. So, we had decided to look into some of these cases, and how much time I have? Okay. So, So, okay, this was then termed as the improper hydrogen bond. So, we had an anti-hydrogen bond, now it became the improper hydrogen bond. So, the question that we wanted to answer was, what is the nature of CHX hydrogen bond, whether it is anti, improper or just another hydrogen bond. Okay. So, this is these are the systems that we looked at, the haloform complexes with the phenol derivatives, larger aromatic bases like indole derivatives like 3-methyl indole, 7-aza-indole. Then there were imidazole derivatives, namely the benzimidazole and the methyl benzimidazole complexing with water, alcohol and ammonia, etc. And then there is a highly activated CH group in 1,2,4,5 tetracyanobenzene with the water alcohols and amines, etc. So, here the idea was that the chloroform CH could bind to the oxygen center, the pi density, because of the methyl group could positive inductive effect could increase the electron density here. If you change that to the cyano group, how would that change? That was the objective here. Here there was a larger aromatic electron base, and whether the CH pi interaction would be centered on which one of these was the question to be asked. Benzimidazole, I will come to that. There is a CH group here which is mildly activated. The idea was whether the CH group will act as a hydrogen bond donor, and then of course the tetracyanobenzene here. So, the first, okay, this is the methodology that we form the complexes of the hydrogen bond donor acceptor using the supersonic expansion method. You do the spectroscopic studies using electronic, vibrational, using the laser based spectroscopic methods. You compute the minimum energy structures, IR spectra and binding energies, etc., and compare the experimental and computational spectra to assign the observed structures. So, this is the first piece of data, paracresol versus paracyanophenol. You see, this is the IR spectrum of the paracresol monomer. This is the OH stretching frequency. When you complex that with chloroform, you do not see any change in this OH stretching frequency, just about 4 wave number shift, and you see a new feature here at 3044 wave numbers, that is blue shifted by plus 11 wave numbers compared to the chloroform monomer. And in the fluorobenzene, you see a small peak here, and this is not a noise because this is the average spectrum of several dozens of the spectra, and that is plus 1700 wave number blue shift. So, you see the enhanced IR intensity here and the decreased intensity here when it is a fluoro versus the chloroform. This is the cyanophenol group, and here is the OH of the cyanophenol. This is one of the aromatic CHs. For some reason, it is very strong in the paracyanophenol. So, when you complex that with the CHCl3 chloroform, we get a peak here at 3033 wave numbers, which is 0 shifted from the monomer chloroform CH stretching frequency. And we can do this experiment with the CDCl3, and this peak disappears and this peak still remains. So, that ensures that this peak indeed is due to the CH of the chloroform. So, here also you have the blue shifted when it is complex with the chloroform, and then it is red shifted when it is complex with 0 shifted when it is complexed with the chloroform. So, this is what happens when it is fluoroform, when it is paracresol, the electron density is enriched in the ring, and then you have the CHCl3. Well, these colors are characteristic of fluorine atoms, but this is supposed to be CHCl3. It is pi bound, CH pi bound, that is showing the blue shift. When it is cyano group, the shift changes to the CN end, and this CH is bound to this nitrogen atom, and this gives rise to the 0 shift hydrogen bond. And this is based on the computed binding energies and the IR intensity data, such as increase in the IR intensity. So, one would argue that why do you call it a hydrogen bond? Because A, there is evidence that mass corresponding this species is identified in the mass spectrum. You can do the REMP and make sure that you have the correct assignment of the spectrum, and then based on that you do the IR spectra, and that gives rise to this chloroform feature. So, this is the 3-methyl indole with the chloroform and the fluoroform. Again, these are the RAMP data, which is a categorical assignment to the mass corresponding to the methylbenzimidazole, methyl indole plus chloroform and fluoroform, and then you do the IR spectra. Again, here with the chloroform you find that the intensified peak here at 3035 wave numbers. In CDCl3 that peak disappears, that ensures that confirms that it is indeed the CH of the chloroform. And if you compute the structures with chloroform, you get 3 different isomers, and one has to then figure out which one of these is what you see in the spectrum. And this is a comparison of the computed IR spectrum with the observed IR spectrum, and you find that the structure 2, which is this one here, that agrees well with the observed IR spectrum. So, here again it is a CH pi bound hydrogen bonding interaction. That is plus 2 wave numbers. With the fluorine CHF3, it is blue shifted by about 16 wave numbers. So, again the fluorine is giving a higher blue shift compared to chlorine. So, here we have the chloroform complexes. I am not going to go through all of these. You have with the 3-methyl indole you have 2 wave number, with the cyanophenol we have 0 shift, and with the 7-aza indole we have as large as 89 wave numbers red shift. CH-N interaction has been known to be strong, and that gives a very large red shifts. And of course, this nitrogen is different from this nitrogen. This is a cyano group, which is a CN triple bonded CN. So, this is not going to give you red shift compared like this, but this kind of a sp2 hybridized nitrogen atoms you get a very large red shift. Here the fluorine bound complexes, which all gives uniformly the blue shift, although the degree of blue shift changes. Methylbenzimidazole, the benzimidazole and the methylbenzimidazole, the idea was that you have these 2 donors and acceptors, and then here CH is a mild kind of a donor. So, you wanted to see if the CH can indeed work here as a hydrogen bond donor. And when we added water into this chamber in the sample holder, you get the mass spectrum just lights up, and you get this huge number of water clusters complexing with the benzimidazole. And this was interesting. So, so what we did was, this is the benzimidazole water 1 clusters, and you see the number of peaks here that corresponds to the RAMP data of multiple conformers of the 1:1 complexes, and these are the IR data. Okay. So, this is the NH stretching frequency of the benzimidazole, that is this guy here. So, in one of the complex this is disappeared, but there are 2 features here corresponding to the OH stretching frequencies. So, that tells you straight away that this complex, this feature A prime is due to the NH O bound complex. These 2 features are because of this OH is donating to the nitrogen atom, because this NH frequency is intact. So, what has happened is that in this 1:1 complexes, this CH is just a spectator, it cannot compete with the conventional NH acceptor donor. When you go to the higher MERS, like this is the W2, water 2, these are the spectra of the these 2 conformers. But in addition, this particular feature gives you number of features here, and that gives you the enhanced CH frequency here. Okay. So, that is telling you that the CH is acting here as the involved in the hydrogen bonding thing. If you compute the things, you get number of different conformers, but then we did all the work and figured out that it is this particular conformer that is observed in the beam. So, with the benzoxazole, benzimidazole and the methylbenzimidazole, these are the structures where the CH indeed takes place in the hydrogen bonding. However, it is not a primary driver, but it is a secondary hydrogen bonding player. Higher clusters also you will find that the CH does take role in the hydrogen bonded ring here, but these are all blue shifted hydrogen bonds. Now, this is the last one that I will give you the example, tetracyanobenzene. You have 4 cyano groups attached to this benzene ring, making the ring highly electron deficient and rendering this CH highly electropositive. This hydrogen is partially positively charged. So, that gives you multiple opportunities for the solvents to bind to this complex. They could bind to the CN hydrogen acceptor with the hydrogen bond donor, CH as a hydrogen bond donor and the oxygen as acceptor. You have electron deficient ring here. So, the electron rich substance like water could be binding with the oxygen down and the OH bonds hanging up. So, there are multiple options here, and Sanat did all the work with this tetracyanobenzene. He is also the co-author of this review in this issue. So, we did number of different solvents, water, amines, sulfur centered compounds, etc. So, this is the TCNB alone, this is a REMP data, LIF data, and when you add water, you get number of features here telling you that the number of different conformers are forming here. Either number of different conformers or the different higher complexes, water, this is 1:1, 1:2, 1:3, etc. So, these are the IR data for the bare TCNB. This is for the feature A, which is the first one after the this guy here, A, B and C. So, you see that A, B and C have different IR spectra, and the number of features here in this OH antisymmetric stretch are increasing. That gives away the clue that there are number of water molecules present in this particular complex. So, here we have, this is eventually assigned to 1:1 complex, where the CH frequency is enhanced compared to the monomer and redshifted by about 8 wave numbers. Here this is 1:2 complex, where the CH frequency is further enhanced and further redshifted, and this is 1:3 complex, where it is moved so much closer to this another CH overtone of the CH bend, which gets enhanced because of the Fermi resonance. So, if you look at the finally what we concluded was CH to 1:1, CH is the primary hydrogen bond donor for this oxygen atom. Here it is a water chain bound to this CH anchor and then closing onto this nitrogen center, and in water 3 it just becomes bigger and bigger and then completes this on the nitrogen atom. And the binding energy increases not as a multiple of 5 kilocals, but higher than the 5 kilocals, multiples of 5 kilocals, telling you there is a fair amount of cooperativity in the dimer and the trimer. So, the number of different things that we did, solvents we did, these are the excitation spectra, and that tells you there are a number of different clusters formed into this with the TCNB. These are 1:3, 1:1, 2, 3, 1:1, 2, so on and so forth. And we do the IR spectroscopy and all of these, and what came out was with TCNB, be it oxygen or nitrogen or the sulfur, in all the cases the CHIR was, stretching frequency was redshifted by the amounts indicated here. Correspondingly, the CH bond length also increases, and that is behavior analogous to the conventional hydrogen bond. Okay. Now, there are other characteristics that they should be following the acid base formalism. What it means is that the CH redshift should scale with the proton affinity of the acceptor, and this was also observed in this particular case. There are other correlations that were shown here, binding energy scaling with the proton affinity, orbital second order of perturbation energy also scaling with the proton affinity. So, this is showing all the characteristics of the conventional hydrogen bond, although it is a CH hydrogen bond. So, we were wondering as to what do you learn from here, and this is the summary slide where you have the chloroform based CH hydrogen bond donor with a number of different acceptors, and in these two cases it is a red shifted thing. In cyanophenol it is 0 shifted and the cresol it is blue shifted. Fluoroform is uniformly blue shifted, benzimidazole is blue shifted, TCNB is red shifted. What is it? What makes this happen? So, if you look at the NBO charges on the carbon and the hydrogen, what happens in the chloroform is this is the regular dipole that you have, like one you have in a conventional hydrogen bonds. In the fluoroform, the carbon is more electropositive than the hydrogen. So, the electron rich guy which is approaching the CH, probably it attracts carbon more than the hydrogen. So, it causes the red shift, blue shift here. Benzimidazole, again it is the same situation, and TCNB you have the again similar situation as this, and this gives you uniformly redshifted hydrogen bonds. Now, in unconventional hydrogen bonds then, the questions are which way is the dipole here, electron density whether it is moving into the anti-bonding or elsewhere, and what will happen to the X-stretching frequency is the thing that one needs to think about. So, this is the Jemis has published this paper some time ago, the red, blue and no shift hydrogen bond. I think he is going to give talk about this in none other than the hydrogen bonded systems. So, what he said, well, he had looked at these various parameters, and whenever the hydrogen bonding situation is involving hydrogen OH group, OH always elongates when the complex is formed, because OH being the dipolar the polar bond, it is a very short XH bond, 0.95 angstroms or so, whereas SH or CH, the average hydrogen bond is not hydrogen bond, the bond length of CH or SH is longer than 1 angstrom. So, in this situation, because it is the dipolar, if the positively charged hydrogen, whenever it is coming in contact with the electron rich substance, it gets further elongated, invariably leading to the redshifted hydrogen bond. Whereas in this particular case, it will depend on the situation, and what he is shown here is that depending on the strength of Y, that is the hydrogen bond acceptor, in case of the HF or the OH, you will find that the XH bond length always increases regardless of the strength of the Y, but whereas in the case of CH, depending on the strength of the hydrogen bond acceptor, one could have the red shifted as well as the blue shifted hydrogen bonds. So, this is what the take home message is from this work. So, in summary, I would say that the chloroform complexes uniformly blue shift, whereas chloroform complexes show omnidirectional shift. This is CH is not highly activated enough to compete with the conventional hydrogen bond, but the second water molecule gets anchored in CH moiety. TCNB is almost behaving like a conventional hydrogen bond donor. Direction of CH redshift depends on the direction of dipole. CHY interactions followed by the acid base formalism, at least in the TCNB case, and CH bond is like any other hydrogen bond, nothing improper about it. I would say rather than calling CH, it should be called XH hydrogen bond, no matter what character this X takes, but then the shifts can be. Interestingly, we had done some work long time ago on the hydroquinone argon molecules, and when the argon is attached to the OH group, computed frequency had shown the blue shift. So it is possible perhaps with the OH also one could blue shift. So, these are the people whose work I presented here at some point or the other. Ajay and Sachin, they keep my lab running. The funding comes from DAE through TIFR, and thank you all for the acknowledgement, and thanks Arunan for the opportunity.
Hello. So, when you are comparing the experimental higher frequencies, so shifts in one slide, I could see that the +2 shift is there.
Yes.
So, what is the value that you give importance to the shift? Because isn't it too low for the resolution of the higher data?
No. In these experiments, the resolution is very high. Our resolution can be less than 1 wave number.
Okay.
Yeah.
And the second
Because
question
these are all
is,
laser based spectroscopy. So, the laser line widths are very small. So, one can have one wave number for sure. So, the 2 wave number could be 1 or 3, but it can definitely not be 0, that is for sure.
and the second question is regarding the zero shift. If one concludes from the IR data itself only that my zero shift corresponding to there is no hetero interaction is going on, then what kind of mistake he or she will be doing?
Well, the IR shift is the data that I showed here, but there are lot many things go into this experiment. A, you are conclusively identifying the mass corresponding this complex, 1:1 complex. Then you do the excitation spectra, S0, S1 spectra, identify the features in the excited state corresponding to this particular complex, tag that feature, and then you do the IR spectroscopy, that then you definitely know that this is the IR spectrum corresponding to this mass and this particular excited state, and then aiding that with the computational data, the binding energy, the most stable conformer. Using all that information, one can say that this is the hydrogen bonded.
So you need to do various other experiments.
Various other things one needs to do.
Just on a side issue, so you mentioned the benzimidazole water complex that you studied, and you saw the isomer where you have the pyridinic nitrogen form a bond to the acceptor proton from the water. Did you see the other possibility where the water attaches to the pyrrolic site of benzimidazole?
Which side?
Can we go to this slide? Yeah.
If better.
We got benzimidazole. Is the
Yeah,
molecule. Right. So, okay, that's.
This is the OH donating to the nitrogen. Okay, this is the
that's
oxazole, but
not- yeah. Okay, so did you see a possibility where you have one water attached to the other nitrogen site on the benzimidazole?
oh, this as well. Okay, one binding here, another binding here.
Yeah.
Well, here what has happened, this is the global minimum.
Yeah. Okay.
That conformer is also a stable conformer, but one of the limitation of the supersonic jet is that when you are trying to expand and form these complexes,
Yeah.
unless you make efforts, you could end up always in a global minimum structure. So, although this is possible, in our experimental condition, we do not see that, we do not form that. So, we only see this. But if you can increase, so these beams are typically of the order of 5 degrees Kelvin, 2 to 5 degrees Kelvin. But using various other buffer gas such as nitrogen, one could raise the beam temperature to say 10 K or 15 K. And then
So I'll present the data tomorrow, or we could talk later. So we've got some microwave spectra, but here we only have one water. But in the microwave spectra, we've got we've measured spectra where we have one water attached to the pyridinic site, or one water attached to the pyrrolic site, but that's in an argon expansion. But I'll show you the data and we can talk about it.
I think, I'm sorry, just answer in 1 minute. See, this is the benzimidazole, but there is another imidazole derivative where the phenyl ring is attached to this carbon or this carbon, right. In that particular case, this is the data on the IR absorption in slit nozzle. There they propose that you see this as well as this, but we had referred to that paper and we said that this is the global minimum. Yeah. So this is true, it's possible. Yeah. But what happens is here you see number of hydrogen bonds is 1, 2 and 3. So you have more, this is a more global minimum. There you would have just 1 bond and 2 bonds. It's just a number of.
Thank you
Okay.
again for